given the All right, while Shaurya is getting set up, our next talk will be given by Shaurya Gomber, also from UIUC, and he'll be talking about evolving abstract interpreters.
Hello, am I audible? Yeah. So hello everyone, I'm Shaurya, and now that we have seen how abstract transformers can be generated from LLMs, I am here to talk about what are some inherent limitations in current abstract transformers design and a new paradigm of abstract transformers called the evolving abstract transformers, which we propose to counter those limitations. So as we all know, abstract interpretation works by representing concrete states, a set of possible concrete states, using these elements in an abstract domain. Here, for instance, we have these shapes in the interval domain. And when you have to propagate these abstract elements through the program, you have these specialized functions. For here we have the intervals, the difference of the intervals, and these specialized functions are called abstract transformers. So there can be many abstract domains. We saw an example of the interval domain. Octagon domain has the intervals as well as bounds for the addition and the subtraction of variables. And then there is this Polyhedra domain which allows you to represent state with arbitrary set of linear inequalities. And it's a known fact that as expressivity of the domains increases, this task of transformer design increases, the complexity of transformer design. And these complexity, the task of coming up with abstract transformers, like it has to do with three main things. First, the abstract transformer should be sound. So that means that the output abstract element should cover all the possible post states, and this is needed for the correctness of the analysis. The second thing is precision. So there can be many sound outputs, but you want to have as small outputs as possible for precision of the analysis. And efficiency, if you chase precision, then most of the times you end up spending a lot of time while computing a transformer. So coming up with or implementing abstract transformers is this task of always being in the sound space, but then this balancing precision and efficiency. So we identify three inherent limitations of this design, and I'll go through them one by one. First, the current transformers are per domain and per instruction. So what do I mean by that? There are, as we saw, many abstract domains. We just saw three, but there are like many infinite, there are many abstract domains. And at the same time, there are many concrete instructions, for instance, assignments, meet with guard, guarded assignments, and so on. And coming up with abstract transformer means you have to implement a new transformer domain for a new abstract transformer for each domain and instruction. So this means that you have to spend a lot of time, or nowadays spend a lot of tokens to come up with all these transformers. And this results in these thousands of lines of complex implementation that are there in the current libraries. Furthermore, the current transformers are instruction specific. So what do I mean by that? If you see this two-line program, if you have to abstractly interpret this currently, for instructions, the transformers are implemented separately. And then while doing abstract interpretation, the result is composed. But it is a known fact that precision is non-compositional. So even if both those transformers are as precise as possible, the final result can be not the most precise. For instance, here, this block preserves this difference of x minus y. So if you see in this block, x and y are both updated by y. But if you interpret it one by one, we don't see this captured. And so this requires sequence-aware abstract transformers. But as we have discussed, even coming up with transformers for single instruction is tough. But now we have these sequences which makes it tougher, and also we have more things for which to design the transformers. Finally, we have this fixed precision efficiency trade-off. I'll spend a bit more time on that. So let's consider this example. And if you see in this example, initial value of x is 0. The loop body decrements x by 1. And so it's easy to see that x less than equal to 0 is a valid loop invariant. But when we analyze this program with the Octagon analysis and using a state-of-the-art library, we see that this analysis is not able to prove the assertion. And when we investigate, we see that this transformer for x equals to x minus y is imprecise. Now, ideally, you would want to compute the most precise output at each step, but that is expensive. So consider this input for the abstract transformer and say we have to compute the most precise output for this case, and just focus on this bound. So this task requires, so the new value of x minus y is the old value of x minus 2y because x is now updated to x minus y. So this task requires calling this LP solver to get this bound, and of course LP solver takes time to compute. And we have to do this similar time consuming task for 8 bounds here, and in general for octagons you need these O(n square LP calls for getting the most precise output. So current libraries do not do this, but they instead fall back to these cheaper and less precise heuristics. One of them is interval relaxation. So interval relaxation heuristics just ignores the relational constraints and just computes an interval relaxation answer. And the answer, if we observe, is sound, but it's less precise. And this imprecision that arises here propagates throughout the program, and that makes the difference between the assertion being proved or not. So essentially, what happened here was that the libraries prioritize efficiency over precision. But different tasks have different precision efficiency requirements. So if you have a task which requires this quick turnaround time, like a CI/CD task, then you might want to spend less time and be okay with a less precise answer. But like if your task is a safety critical task, like if you have to verify a program for some rocket that's going, then you'll be okay with spending more time, but would want more precise answers. And then there are these plethora of options in the middle. But as we have discussed, the current transformers have very fixed heuristics, and they don't allow you to adapt the analysis as per the task requirements. So having discussed all these limitations, what do we need? Ideally, we need a framework which works across domains and instructions, is sequence aware, and also allows you to adapt efficiency and precision. And here comes our evolving abstract transformers. So with evolving abstract transformers, we provide a unified framework that works across domains and instructions and sequences, and they allow tasks to adapt precision and efficiency by this idea of space of sound outputs, which we'll discuss in the coming slides. So on a overall, how does it work? Like along with the element, it takes the instruction and the abstract domain for which to compute the abstract output. The first step is not to compute a single output, but instead compute a space of outputs. And this space of outputs has this property that for instance, this octagon family, all octagons which you can instantiate in this family are sound. And once you have that, you can use traversal techniques like gradient guided traversal to instantiate these. So if we see, like this technique works for, like this example was for octagon domain, but our technique supports all polyhedral domains, which are the domains where abstract state is represented using a set of linear inequalities. For instructions, our evolving transformers support all instructions which have linear updates, quadratic updates, and also meet operation with linear guard constraints. So this already gives us these two benefits, that now we have a technique which works for domains and instructions and is also sequence aware. Now we'll talk about how we solve this precision efficiency trade-off problem. So for this, our first key idea is instead of instead of computing this single output, for instance here, you should instead compute a space of sound outputs. For instance, like this green space is a space of sound outputs, and all the outputs that you instantiate, all the octagons that you instantiate from this space will always be sound. And once you have such kind of a thing, tasks can now adapt and pick outputs that suit them based on their needs. Now we'll discuss how can we capture such a space. So this is our running example, and we saw that to compute the most precise bound, we need to call an LP solver. But the key observation is that if x minus y less than equal to C sharp is the most precise, any bound which is greater than C prime results in a sound output. So our problem boils down to, can we get a space of bounds which is greater than C prime for this problem? And here duality can help us. So how does duality work? Like first we get these constraints into standard form, and duality works by introducing these Lagrangian multipliers for each constraints, and Lagrangian function is just with the objective, we multiply all the constraints with the Lagrangian multipliers and add them to create this unconstrained optimization problem. And Lagrangian dual is the maximization of the Lagrangian. And all this gives us this property that for all positive multipliers, this G lambda is greater than or equal to C prime. So using this, we kind of have a sense of how can we capture this bounds, space of bounds which is greater than C sharp. But when we use this, the standard duality, the space of bounds which we get, the G lambda and the space, it's sound, but it's not very easily traversable. Because if you see, for this small case, we had 5 multipliers and these equality constraints, which makes it harder to sample from this space and also traverse this space. So our task is not only to get a sound space of outputs, but to get an easily traversable sound space of outputs. So that's why we come up with this selective dualization technique. And this is based on the observation that when we are doing abstract interpretation, in most of the abstract domains, we have these box constraints, which are just interval constraints on the variables. And the remaining constraints, we call them as the relational constraints. So in selective dualization, we dualize only the relational constraints. So we only introduce the multipliers for the relational constraints. And you can see this already gives us the benefit that we now have less multipliers. And now again, we construct the Lagrangian with these 2 multipliers. And now the interval constraints, which we did not have the Lagrangians for, appear in our Lagrangian dual. So they constrain the space on which we have to maximize the Lagrangian dual. And then using some specialized bounding procedures that we describe in our paper, we get this space, which again is sound. But if you compare it with the space that we would have gotten from standard duality, it has lower dimension, it has less number of constraints, and it has easier constraints. So now this space is easier to traverse than the previous. Before going to traversal, let's discuss about the properties of this space. So if you consider like this, and this G and the parameter space, and if we just sample some values from this parameter space and compute the bounds, you can see 5 examples instantiations here. So there are 3 properties that we see. First, all of them are sound because they are greater than -2. For 0, 0, the result matches the interval analysis result that we had. And also in our space of outputs, we had the most precise output. So in the paper, we formally prove these properties, and these properties are ensured by how we construct the space. Now, once we have such a space of outputs, the next step is to instantiate a concrete output from this space. Because when you are doing abstract interpretation, you can't just propagate space. Once you have this space, you have to pick one element. And here, ideally, if it was easy to pick the most precise, then we would have done that. But here, we instead need some search procedure in which the task can give us some search budget, for instance, R. And then the search procedure should be such that if we have more budget, then ideally we get more precise answers. So as we saw in our example, we don't get a bound, but we instead get this function, parametric bound. And the smaller the value, the more precise the bound gets. And our space is constructed in such a way that these parametric bounds, the space is always differentiable. So what you can do is you can allow tasks to give these gradient steps R. And if there is more time, then we can do more steps and eventually get more precise answers. But the issue with this is we can't just apply naive gradient descent, because we also have some constraints that we have to satisfy. And if we do projected gradient descent sort of techniques, then they become inefficient because of the projection operation. So we come up with this adaptive gradient descent procedure, and it works like this. If we are inside the parameter space, then we can just minimize the bound to get more precise bounds. But as soon as we go outside the parameter space, we steer the search inside the parameter space by instead doing gradient descent on the violations. And because we had this property that at θ0 we have the interval relaxation answer, we can always start our search from that, so that we are always as precise as interval. So pictorially, like the search starts from this interval relaxation answer. we take these gradient steps, keep getting more precise answers, but the time also increases, and we are fine with that. And as soon as the search goes into the space which is not inside the parameter space, for instance here, like the lambda 1, lambda 2 is 1.2 and 0, but we had this constraint that the sum should be less than equal to 1. Then at this point we descend on the constraint violation so that we can undo that, and we again go back to the sound space and eventually reach the most precise answer. So now, like doing this thing of computing sound space of outputs and efficiently traversing it using gradient descent also gives us this benefit of adaptable precision efficiency. Now I'll talk about our experiments. To evaluate, we used NLA DigiBench benchmarks. These are the state-of-the-art benchmarks for affine and nonlinear reasoning. They have these 55 programs, and across programs they have these 237 invariants. So we run our evolving abstract transformers with increasing number of gradient steps, and we evaluate two things. First, overall gain, this blue line. Overall gain is how many invariants got strengthened as compared to the baseline ELINA. And we can see here that as the number of steps increase, the number of invariants that get strengthened over the baseline increases. Similarly, this red line is, for this we computed the most precise outputs using an LP solver based approach. And here we compute that how many invariants are still not up to the optimal mark. And we see here that as the number of gradient steps increase, it eventually reaches 0. So that means we compute the most precise outputs for the linear case. We also compute this marginal gain, which just computes that when we increase the search budget from 1 to 2, 2 to 3, how many number of invariants get strengthened across that. A thing to note here is that when we run this analysis using LP solver baseline, that takes 230 seconds for zones and 350 seconds for octagons. But our analysis reaches there in 70 and 110 seconds, and this makes us around 3.2x faster also than these heavily optimized LP solvers. And that is because we do this gradient descent and jointly optimize the bounds. We also evaluate our framework on quadratic operators, and here we see that even for domains like Polyhedra, we get these precision gains. So looking forward, we think that this framework can also be used for for many other things, like if it can enable GPU-based abstract interpretation, or if your task is to find some specific octagon to prove a property, then you can customize the loss function on which you do the gradient descent. Or while doing program verification, you can do some sort of abstraction refinement that if you see that your property is not proved, you can go back and choose a new parameter from the space. So yeah, this concludes my talk. And now we hope that after this, we don't have to implement a lot number of lines just to do abstract interpretation, and we have this one framework that can do abstract interpretation for many domains and instructions. And our paper and code can be accessed from the.
Thanks, Shaurya. We have time for one quick question.
Is there interest to go beyond like linear transformation, or like can you do it?
Yeah. So as I saw here, we do support the quadratic operators also, but that is because currently our bounding procedure supports linear and quadratic. Quadratic is easier because we can still do it by finding the root. We are also, there is this work in progress where we are also trying to extend this to polynomial instructions as well. What about?
What about exponential functions?
Exponential functions we have not yet thought about, but like if we have this support for polynomial expressions, then we can use Taylor series expansion for exponential functions and support it.
All right. Any more questions? Looks like not. Let's thank Shaurya once again.